Everyone thinks AI compute is about chip speed, but the industry is crashing into an invisible physical barrier, the memory wall. Training a model is a highly parallel process, but inference, specifically the autoregressive decode phase, operates sequentially. It generates one token at a time. For a 70 billion parameter model, generating a single word requires reading approximately 140 gigabytes of weights from memory over and over again. This roofline model plots a GPU running autoregressive inference. The arithmetic intensity is barely one floating point operation per byte, leaving it firmly memory-bound. Adding faster compute cores just raises the roofline's peak, leaving actual performance trapped by how fast data is fetched. The modern processor is starving for information. Escaping this bottleneck requires moving memory off the motherboard and directly into the processor package itself. To close the physical distance between compute and memory, the industry relies on an architecture called CoWoS, chip-on-wafer-on-substrate. Historically, processors and memory chips were separate components, routed together through copper traces on a traditional printed circuit board. That layout imposes a severe latency penalty. CoWoS eliminates the standard motherboard routing. Instead, the logic die and the high-bandwidth memory stacks are placed just millimeters apart on a shared ultra-thin silicon interposer. Underneath those dies, data routes through thousands of microscopic vertical channels called through-silicon vias. This physical proximity allows for massive parallel connections. HBM3E established a 1024-bit wide interface. The upcoming HBM4 architecture doubles that to a 2048-bit physical data highway. Solving the bandwidth bottleneck was not achieved with smarter code. It required microscopically shrinking the physical distance the data has to travel. Routing terabytes of data across microscopic distances carries a severe secondary consequence: extreme thermal density. Heat concentrates aggressively at the die-to-die physical layer. It traps along the logic die's peripheral region, where high-power I/O transmission takes place. Traditional single-sided passive cooling methods completely fail at this new multi-die stack height. A modern logic processor consumes upwards of 700 watts. That lateral thermal energy bleeds over and accumulates vertically within the stacked DRAM layers right next to it. The engineering required to break the memory wall inadvertently triggered a catastrophic thermal wall. Spotting these foundational hardware shifts is how top operators stay ahead of the curve. Understanding the mechanics behind these shifts gives you a tangible advantage. At TechViews10x.com, we help you understand frontier tech and give you the exact strategies to leverage AI in your business and build profitable online assets. Head over to TechViews10x.com to join our community. To prevent silicon meltdown, engineers are deploying extreme localized thermal management directly into the die interface. SK Hynix approaches this structurally by introducing integrated cooling elements, or ICE. These silicon blocks are inserted precisely into the high-heat interface. They capture energy and route it upward, creating an explicit secondary heat dissipation path that bypasses the core die entirely. This physical intervention yields a measurable 30% reduction in thermal resistance. With that heat path established, HBM4 stacks can operate under sustained, high-pressure AI workloads without triggering hardware throttling. Thermal management has shifted from external fans to internal bridges, with heat dissipation paths engineered directly into the silicon substrate. Physical cooling blocks alone cannot handle the thermal load. Managing HBM4 requires real-time, telemetry-driven software intervention. This document details the latency performance of telemetry-guided optimization. It validates that dynamic control actively reduces latency by 12 to 18%. The key is firmware-adjusted timing compensation. The system continuously pulls thermal sensors to map spatial temperature gradients across the package, enabling workload-aware DRAM refresh cycles. Instead of refreshing the entire memory stack blindly, the firmware dynamically increases the refresh rates only on the hottest physical partitions to counteract electrical leakage. This targeted approach eliminates the secondary heat that would normally be generated by unnecessary global refresh cycles on the cooler sections of the chip. The AI accelerator operates as a reactive organism. Firmware and physical silicon negotiate thermal limits in a matter of microseconds, but even advanced architectures like CoWoS and HBM4 have hard economic ceilings. This chart tracks the cost of HBM3E capacity and bandwidth, showing a relentless upward trend. Scaling the horizontal package size to fit more memory destroys manufacturing yields and introduces massive instability into the power delivery network. To bypass the limits of a single interposer, architects are turning to high-connectivity network topologies. This leads to processing near memory, or PNM. Instead of placing logic next to memory, PNM vertically stacks custom 3D logic directly onto the memory integration. Compared to the 2.5D layout of CoWoS, true 3D PNM yields massive power savings simply by eliminating the need to transmit data across an interposer. As horizontal interposers approach these yield and power limits, 3D vertical integration represents the primary path for continued hardware scaling. Ultimately, current designs are constrained by an absolute physical limit, the electrical resistance and heat of copper routing. The final frontier is co-packaged optics. This replaces copper bottlenecks with sharp pulses of light, transmitting massively parallel data directly from memory to compute clusters. Photonics effectively removes physical distance and thermal generation from the bandwidth equation entirely. Optimization has reached a turning point. The bottleneck is no longer how many operations a core can perform, but how fast those cores can communicate. Visit techviews10x.com and subscribe to TechViews 10x for the real tech behind the hype. The performance lead in the next generation of AI will belong to architectures that solve the fundamental physics of data movement.